Okay, I suppose this is technically a review problem, but it is the part of 1051 that people seem to have the most trouble with, so why don't we take our time going through it a little bit just to make sure you have an idea of what's going on. So the question says, find the electric field 1 centimeter from a long line of charge with charge density lambda equals 2.5 times 10 to the minus 6 coulombs per meter. So this is our linear charge density. It's charge over length. So the first thing we think about is this is our line of charge, and my models are a paper towel roll and a bamboo skewer. So the direction of an electric field around a line of charge is linearly outwards everywhere from that line. So if my bamboo skewer is my line of charge, the field here is out, 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 out. So it's out everywhere. It's got that spherical kind of symmetry. I'm going to try and draw it in 3D here. So no matter where you are on this line of charge, the electric field vector points directly outwards. Okay, so I know what the electric field looks like. It's got some spherical symmetry. Next, I need to pick a Gaussian surface with a similar sort of symmetry so that when I do my integral of E dot dA to find my flux, the integral is not difficult. To make integrals not difficult, you take things that are parallel or perpendicular. So what I want is an object that has an area that's either parallel to the fields or perpendicular to the field. The easy way to get that is pick your Gaussian surface that looks like your object. My object is a long line of charge. My Gaussian surface is going to be a long cylinder. So my Gaussian surface is going to be a cylinder that surrounds my charge. The area of my cylinder is outwards everywhere from the cylinder, so it's going to be parallel to my electric field vector everywhere except at the end. At the ends, my electric field vector, my area vector points straight out, my electric field vector points straight up. Those are perpendicular. Okay, I'm going to draw my Gaussian surface next. My Gaussian surface is going to be a cylinder that goes around my line of charge. Pretty often you do those with a dotted line just to show that they're imaginary, my paper towel roll notwithstanding. So my Gaussian surface is a closed cylinder the radius is equal to r. And the length is equal to L. I'm going to take the radius to be 1 centimeter because that's where I'm trying to find my electric field. This length L is a figure I'm hoping is going to cancel because I don't have a length. Okay, let's write down Gauss's law. Gauss's law states that the net electric flux through any closed surface, like my cylinder, is the integral of E dot dA, which is equal to the charge inside my closed surface divided by epsilon naught. So I'm going to figure out the integral of E dot dA first, my flux through the cylinder. I'm going to figure out my Q enclosed. I'm going to put those together and I'm going to find my answer. So the net electric flux through my cylinder has got 3 contributions. It's got the bottom end down here, so the flux through there, flux through the top end, and the flux through the tube parts. When I calculate the flux through each of those 3 bits and I add them up, I'll get my total flux or my net flux. Okay, so my net flux equals the flux through the top part, this part, plus my flux through the bottom, this part, plus the flux through tube part for the lack of a better word. My flux through the top is the integral of E dot dA. Now from the top part, my electric field vectors point out everywhere. My area element, my little bit of area, points straight out of the surface. See, those guys are perpendicular? So the integral of E dot dA is E times dA times cosine 90 degrees equals 0. Okay, likewise on the bottom. My net flux through the bottom part of that surface there, We've got the electric field vectors go up and down and out. The area vector sticks straight out the end, so they're perpendicular. If you need a little refresher on scalar products, I've got a document posted on our Brightspace page. Okay, through the tube of the cylinder, it's still the integral of E dot dA. Let's see if we can get that angle. So for the tube part of my cylinder, if I pick any little element, the area vector sticks straight out, just like the electric field vector sticks straight out. So no matter where we are on that cylinder, the area and the electric field are always equal. So my line of charge has the electric field straight out, my cylinder is straight out. Here it's up and up, here it's down and down. So no matter where we are, the directions are exactly the same, they're straight out. So that's the integral of E times dA times cosine theta, where theta is 0 degrees, and of course the cosine of 0 is 1. Okay, this integral simplifies a bit. My electric field is a constant anytime I'm a constant distance away, so I can take my E outside. Integral of dA is going to give me A, where A means the area of the tube part of that cylinder, which is 2 pi r times the length. Okay, so for my net electric flux, I've got 0 plus E times 2 pi r L. Okay, that's the part I'm going to plug in right here. What about for my Q enclosed? Well, I can use my charge density to figure that part out. So my Q enclosed, let's just get the picture back down here. My Q enclosed is the amount of charge inside my cylinder that I drew with my blue dashed line. So it's the amount of charge on this much of my long line of charge. So how much charge is on this bit right here? So that's my Q enclosed by my cylinder. I can find that using my charge density. So that's my charge on the line. It has the same length as my cylinder, of course. That's going to be my charge density times the length of the line, because linear charge density is charge over length. Okay, I'm going to put my Q enclosed in here. I'm going to put my net flux in here, and then I'm going to see what that gives me for my electric field vector. So E times 2 pi RL equals lambda L over epsilon naught. Let's get my E on the side by itself. I see that I've got an L on both sides, so they can cancel. E equals lambda over 2 pi epsilon naught times 1 over r. Electric field is a vector, of course, so the direction is radially outwards. Now, we were asked for a specific value at r equals 1 centimeter, so I'll put in my r equals 1 centimeter next to get my answer. This is my expression. So my lambda was given, that's 2.5 times 10 to the minus 6 coulombs per meter. I'm going to divide that by 2 pi times epsilon naught. Pretty sure I got my units right there. R I'll have to put in meters, of course. Put that through the calculator and I get 4.50 times 10 to the 6 newtons per coulomb, and the direction is radially outwards. The nice thing about Gauss's law is we did a problem like this. We found the electric field above a line of charge, but we did it with the integrals. This is a really fast way to do it, and you can use Gauss's law whenever you have that kind of symmetry in a problem.